My talk today is titled Listening Through a Vibration Motor, and this is essentially with my student Nirupam Roy. He did most of the work, I just take the credit, and any questions I should be able to answer most, but feel free to ping him as well. Getting started, almost all of you, actually I would even say all of you have devices, mobile devices on you, and all of them has what is called a vibration motor. This is that device that makes your phone buzz or your Fitbit buzz or your watch buzz whenever there's an alert for you or some kind of a notification. Now we've been playing with this vibration motor for a while now, and if you zoom in into what this vibration motor has inside it, you will realize that it's actually a small magnetic mass that's positioned inside a coil, and when you drive electrical voltage through this coil, there is electromagnetic field generated inside this coil which makes the small magnetic mass move back and forth. Okay? So if you drive AC current, the frequency of that current and the magnitude of that current would actually modulate the motion of that magnetic mass, and therefore you can programmably control that magnetic mass and thereby your vibration motor. Okay? None of today's devices do much of that because essentially they're used for giving you a 1-bit information that, oh, a message came in. So it's being very underutilized in terms of what it actually is capable of doing, but we're starting to look at this, this actuator as a new platform for doing interesting things. So we have a project called Ripple that's ongoing in our lab where we're essentially trying to develop a new kind of a modem that uses vibration as a method of communication. So our goal is kind of, if one phone touches another phone, and if the second phone has an accelerometer or a microphone, then the phone that touches this phone, which has a vibration motor, can be essentially convey information, transfer information using physical vibrations. So the phone that has the vibration motor vibrates all the bits of information, and the phone that is the receiver encodes this vibration through an accelerometer or a microphone, decodes the bits of information, and gets useful information out. And we've kind of developed a ring, a finger ring, which you wear, which has all your passwords and stuff loaded into it in the vibration motor. And whenever you pick up your phone, the vibration actually passes through your finger bone, touches the phone, and the phone's accelerometer microphone picks up this vibration and automatically authenticates yourself. You don't have to punch in your passwords anymore. And the idea over there is because vibration doesn't leak information like wireless signals do, there are some security benefits in communicating through vibrations. So that's a project that's ongoing, but while we were playing with these vibration motors and microphones, in many a case we started playing sounds near our hardware table, and then we started realizing when you actually play sounds, the vibration motor also vibrates in a way that you did not expect it to. Even though you're driving the vibration motor with a specified voltage, what comes out of the vibration motor is actually not what you're expecting, it's something different. And then as we started looking into this, we realized, whoa, the vibration motor actually responds to people talking around the vibration motor. And if you can do something with that signal, you might be able to decode what is being said around the vibration motor. And that is kind of weird because the vibration motor is supposed to be an actuator which does things, and now you're treating that as a sensor which listens for you. Okay? So the goal of this paper is, can we recover speech from the vibration motor, okay? Which is not the intended purpose, and in that sense it's a side channel. Okay? So of course it could be treated as a threat, because now you could imagine if your phone starts having this capability of pulling data out of the vibration motor, you can, a malicious app can stay in the background of the phone and start listening to conversation even though the app does not have access to the microphone or the speaker of the phone. Okay? Now, it's not only a bad thing, there's also a good side of it. It could also be an opportunity where the Fitbit that you wear, which also has a vibration motor, could now potentially take voice commands. You could say, Fitbit, show me the number of steps that I've done, or tell me something about what I'm doing wrong, and it could potentially interpret that command and even give you haptic feedback through the vibration of the device. So the vibration motor could act as both a listener and an actuator both, right? And something more interesting perhaps is we've seen that when you actually touch your phone on your cheeks, the vibration motor picks up the vibrations of your throat and the vocal cords along with the vibrations that come from your acoustic speech, and together, along with the microphone, it can act as a beautiful MIMO system that can boost the SNR of your speech and thereby give you some benefits in acoustic communication. Okay? This paper focuses only on understanding the capabilities of how much the vibration motor can decode. The apps that can be superimposed on top of this capability is not the focus of this paper. So we're only going to focus on what is possible with this. Okay? So to go forward, let me quickly tell you a little bit about human speech and how it translates to a spectrogram. So this is what you get from a vibration motor, but this is the actual microphone recorded speech, and we somehow need to move from here to here. That's the goal of this paper. Okay? So again, human speech is very complicated. I don't understand most of it, but we've tried to abstract out the key aspects for this project. So human speech essentially is made up of two fundamental components. One is called the voiced components, and the other is called the unvoiced components. And these form the basis of the acoustic signal. Right? The basis meaning any acoustic signal can be thought of as a linear combination of these basis vectors, and these are the signals that make up human speech. Okay? Now the voiced components are essentially generated by something called a glottis, which is a part of your throat behind your tongue, which actually opens and closes in a desired manner to generate certain frequencies called the voice signals, and they are like harmonics. There are particular frequencies that are generated, and the harmonics are also come along with them, and they contain vowels and alphabets like B and G and and O and all these kind of sounds. On the other hand, the unvoiced components are more like noise, but they are also important to making up the speech, and they are sounds like S, F, these kind of sounds, and they are this part of the spectrogram. By the way, this is a spectrogram with frequency and time, and the unvoiced signals make up this part of the spectrogram, and then all of this together is modulated and weights are added. Some parts are emphasized, some parts are de-emphasized, tones come in. All of that is done by your vocal cord and your mouth and nasal cavities. They all modulate that signal, and finally one complete signal, acoustic signal, comes out. And here is an example where the person said entertainment, and this is the spectrogram of that spoken word entertainment. Okay? Now in the acoustic community, they have modeled this whole system in a much more complicated way, but I've abstracted out the basics. They've modeled this as a source filter system where there are these bases of the acoustic signal, voiced and unvoiced, which makes up the sound source. Then the vocal tract response is an addition on top of that sound source, and then that's the original speech. And then when that speech impinges on the vibration motor, you can think of that as another response of the vibration motor on top of that original speech, and that finally gets recorded by the vibration motor. Okay? And all we are trying to do in this paper is essentially saying, can we undo what the vibration motor did to that speech? Okay? Good. So there are three key challenges in addition to several engineering and hacking that we needed to do. The three key challenges are as follows. First is high frequency deafness. The vibration motor is a pretty stiff and pretty a device that is not meant to listen to human speech. So if this is the actual vowel A recorded by the microphone, this is what the vibration motor records, where many of the stuff in the higher frequencies, they just don't come up, they just don't show up. For noise, there's not enough response, there's not enough sensitivity of the motor, and so forth. So that's a big challenge, because this part of the spectrum would still contribute in forming the human speech and decoding it. Second, the vibration motor is made out of a device which has a resonant frequency which is within human speech range. And the resonant frequency is around 200 hertz. And microphones, on the other hand, they're very carefully designed so that the resonance frequency of these diaphragms, which actually vibrate inside a microphone, they are outside, they're designed to be outside of the human speech range. So that again affects the signal. And third, there's a higher energy threshold. The material is much stiffer than the actual diaphragm of a microphone, and therefore the SNR that you get with the vibration motor is actually much less compared to the microphone. Notice that this is 40 dB, this is actually 20 dB, and still it's pretty low, except for certain resonant frequencies where non-linearities kick in and the signal actually goes haywire, but after the resonant frequency it again comes back and it's pretty low. So these are the kind of signal challenges that come into the system, and then the idea is to undo some of this to the extent possible. Okay? So we call our system vibraphone, and here's a kind of a quick system overview. To recover the human speech, there are two essential steps that we have to do. One we call pre-processing, essentially cleaning the signal, doing things to the signal so that we get as much of a sanitized signal as possible. And then the other part is speech synthesis, where we essentially take human speech grammar and apply it on the signal, because human speech does have a very nice grammar and we should be able to leverage that to our advantage. Okay? And under pre-processing there are techniques like frequency equalization, background noise removal, speech energy localization, and under speech synthesis there's voice source separation, there's speech reconstruction. Okay? Again, some of this is dry, but I'll quickly go through it. All of the details are in the paper. Even if you do not follow this completely, it's okay, and then I'll get to the results and I'll show you what can be done out of the system. So let's start with speech energy localization. So again, as I said, there are these harmonics in the lower frequencies, but at the higher frequencies you don't see anything. Okay? But humans cannot generate sounds that are narrow band tones that sustain for small durations of time. You cannot generate very quick, high frequency narrow band tones. Typically there tend to be a nice drop off in terms of time and frequency. Now once that is true, then we say, okay, if we actually do a correlation or an autocorrelation of the signal using this frequency window, and we keep moving that autocorrelation window, where all the signal spikes are likely to be the place where there is some acoustic human signal in the time frequency diagram. Okay? So once we realize that there are some signals over here, we said, okay, that's a first hint that we know that there is some signal even though we don't see anything visibly or electronically. Okay? And then what we do is we say, okay, this signal is really polluted by a lot of background noise. Many of that noise is not zero mean. There's like offset noises from the device, from the ambience, so forth. So what we do is we take some of the noise from the sides of this signal and subtract that noise from the entire signal where we know that there is human signal, and that is called spectral subtraction, and there are standard textbook formulas to do it. It's not at all difficult, and once you do that, you basically come to a situation like this where you have an idea, a rough idea, an erroneous idea of where the human speech is in the time frequency spectrogram. Now, because you did that subtraction, the noise subtraction, there are many places where there are not human signals, but you actually see signals. So there are false positives and false negatives. So what we do is we do a clustering on this signal and say, okay, where are the dominant signals? And everywhere else, we basically zero force it, saying, let's only take the places where we know with good confidence that there is human signals over there. Okay? This is called the energy mask. It does not have the harmonic structure anymore, but it gives us an idea of where there is human energy in the spectrogram and where there is no energy at all. Okay? Good. So that's the side of pre-processing. So we have an energy mask that comes in from pre-processing. And then we do speech reconstruction, where the first thing we do is try to understand or replicate the voiced and unvoiced speech structure. And what we do is we say, oh, look, there are these harmonics in the lower frequency bands. We basically replicate those harmonics in the higher frequency bands. It's kind of a blind replication. But we've also seen that the vibration motor's responses, the human speech's response at the higher frequencies actually have exponentially decaying magnitude. So we replicate these harmonics with lower and lower magnitudes with an exponential decaying function. So now we have some kind of the basis for the human speech that we've recorded, because we have some idea of the basis in the lower frequency bands, and then we combine the energy mask and the synthesized signal together to form what we say, okay, this is what our speech signal will look like when recorded through a vibration motor. Okay? This is again an energy mask. It is not an exact idea of where the signal is, but it gives us a reasonably good understanding of where the signals are, and these harmonics come back because you're essentially multiplying the signal with this energy mask, a bit mask. Okay? So this is an example of the output. This is the raw time domain signal, the raw vibration, very bad. This is after all the processing that we do the inverse FFT, and then we get this time domain signal, and this is the microphone generated signal, which is the actual signal recorded from the human's phone. Let me play you an audio demo over here, just to give you a sense of how good this reconstruction is. So this is the original song that we recorded. I hope this plays. Mary had a little lamb. And this we played 1 meter away from the vibration motor. Okay? This is what the raw motor signal looks like, sounds like. So you see, even in the raw signal, there is reasonable amount of information there. I'm going to play that once again. And here's what we get after. Okay, so that's kind of a quick snippet of what we can get out of this vibration motor on your phone. And and there are many other examples that's on our webpage that I'll point to. Sorry about that. So quick evaluation. I see that there's only 1 minute left. We have two evaluation platforms. One is a custom hardware where we bought the microphone chip and the vibromotor chip that's actually used in phones, but we actually used our own amplifier circuit to kind of amplify the signals, and then we process that. And the other is a real smartphone where we've connected the output of the vibromotor to an ADC, which is part of the acoustic processing pipeline. Okay? Today's vibromotors don't come out. The vibromotor in the phone does not have an output. So today's vibromotors cannot be hacked. Your phones cannot be hacked. But there's only a small soldering needed to be able to actually pull out all the signals from the vibromotor. And for a person who does soldering well, it's a matter of 2 minutes to do that, really. Okay? So platform of evaluation essentially is we make people say things near our platforms, and then we get the recorded signal and we ask either humans to decode what was being said, or we ask automated speech recognition software from Siri and Google, and we ask them, what do you think the word was? So we do both human, manual, and automated speech recognition evaluation. So automatic speech recognition results are as follows. The top line shows microphone, which is kind of our upper bound. This is what our process vibration signal, vibraphone, is doing. When you speak on a mobile phone and when you hold it against your cheeks and you speak on the phone, the sound pressure levels are typically 80 to 85 dB SPL, SPL being sound pressure level. So if you're holding it on your cheeks and talking to someone, your vibromotor can essentially figure out the words with an 85% accuracy, even with an automatic speech decoding software. Okay? If you do human, we did two kinds of tests in which we asked one human, what do you think was this word? And in another case, we took a group of humans, let them decide, let them discuss between themselves and come up with one word that they think that that vibraphone decoded. And in this case, you see that the human decoding capability is actually even better, even at lower sound pressure levels. So even if you're 3 meters away, we get an accuracy of around 80% in terms of decoding the words that were being said. Okay? Here's a word cloud of bunch of words that, here are the top 10 correctly decoded words by the automatic speech recognition software. So intuitively, longer the word, the easier it is to detect by the vibration motor. These are the top 10 incorrectly detected word, and smaller the word, it gets harder. Okay? We have lots of examples in the website, in the project website, where you can go and check out what are the different words and how they actually come off when they're recorded by the vibration motor. I want to quickly close a couple of points of discussions. Vibraphone cannot launch on your phone today because vibration motors don't have the ADC connected to it, but it can be done very easily. We do not have a notion of optimality over here now. If you ask me, what's the best you can do with the vibration motor, I cannot give you a good answer. All I'm going to say is microphone is our upper bound, and we are trying to achieve that. We have sidestepped the energy question at this point, and applications are something we are thinking about, but we don't have a killer app at this point in our mind. I must say that there are a good amount of work in this area. We are not the first one to do this. Gyrophone from Stanford a couple of years back showed that if sound is played on a phone, near a phone, the gyroscope of the phone actually responds to that sound. And Axelword, I think last year, MobiSys showed that even the accelerometer has a response to this. But both of these, Gyrophone and Axelword, they all do machine learning in the sense that they know the word that they're looking for and they pattern match with the signal that is getting recorded. Whereas what we are trying to do is to completely do speech construction from ground up, and in the sense that the automatic speech recognition software can decode it. Okay? And of course, there's this work from motion microscope where I'm sure all of you have seen this YouTube video on the TED Talk, where if a sound is played near a pack of chips, the chips' wrapper vibrates and the camera can look at the vibration and pull out what is being played near the pack of chips. Of course, that's a separate, that's a visual technique where the camera figures out what is being played. Ours is, in this case, is a vibration motor, which is completely out of our control. Okay? So to conclude, it's possible to decode speech by decoding the response of the vibration motor. This is not fundamentally surprising because, of course, every object should move when there is change in air pressure around it. But what was surprising was the ease at which we could actually decode some of these signals. We did not have to do much sophisticated signal processing. And importantly, all these decoded words are not through machine learning. It's not a pattern recognition. Any language you speak in, we should be able to record that through a vibration motor and play it, and an automatic speech recognizer should be able to decode these words with reasonable accuracy. Okay? That's all I have for today. Thank you very much.